Hey everyone, thanks for joining today's session on automated disaster recovery for multi-region GenAI applications using vector databases on Kubernetes. Quite the mouthful. My name is Kirsten Foon. I'm part of the marketing team here at Percona. Today I am joined by Sergey Pronin, our group product manager at Percona, and Paweł Bojanowski, principal software engineer at Elotl. And together they will show you how to automate the stages of disaster recovery in Postgres using both Percona and Elotl. Before we get started, though, a few housekeeping items to go over. All lines are on mute for the duration of the call, but you can submit questions and comments to the Q&A box at the bottom left of your screen. We'll get to as many of them as we can at the end of the session, and we'll create a blog post to those that we don't have time to answer. The session is being recorded and will be available for replay in 24 hours. And with that, I will pass the mic over to Sergey.
Hello. Hello, everyone. Welcome. Yeah, as Kirsten mentioned, it's quite a mouthful. I don't want to repeat the title of this talk, but basically what we're gonna be talking about today is running vector database in Kubernetes, and your generative artificial intelligence application might be challenging, especially if you want to also have disaster recovery in place in case your cloud fails or something like that. And today we're going to look into these cases, how it can be fully automated so you can run your database and just do an automated failover. That's it. So this is our agenda. We're going to start with the AI. Artificial intelligence is everywhere, so we're going to just lay out the stage, why we're talking about it, and how vector databases are related to it. Then I'm gonna be talking about the problem space. So, okay, we can run vector databases in Kubernetes, but what's the problem? What are we going to solve? And then Paweł is going to be our problem solver person. He's going to talk about how we can automate the disaster recovery in Kubernetes and even show some awesome demo. And last but not least, we're gonna keep some time for questions and hopefully answers. So let's start. AI is magic. Artificial intelligence is now booming. Everyone is talking about it. There are multiple companies and startups that are becoming unicorns in no time. They're huge. Someone is saying that AI is the new electricity and you should use it today or cry tomorrow, right? So AI is about creativity and imagination for some, but for me, it definitely is because I have 3 kids and they already know how to use AI. Well, I showed them that there are some chatbots that can help you generate these nice images. And they used it to generate this ones, right? And for me, it was almost impossible when I was young to do such things, right? It took me hours to draw something in Paint or Photoshop. And now my kids can use something like Sora. I don't know if you saw this new model, which is text-to-video model from OpenAI, and it's just magical. It can create the whole movie for you out of nowhere. And definitely it's about creativity and imagination, but it's also about some business use cases, obviously. And again, AI is magic, but sorry for Harry Potter reference, but for muggles. When you are on the dark side of IT world and technology world, there is not a lot of magic for you in technology. And you know that it is powered by some powerful technology underneath. And for example, the pieces that powers AI are large language models. That's the heart and mind of modern AI or generative AI. And in turn, large language models are powered by transformers. And if you read some documents or articles about AI, there was this scientific article published, Attention is All You Need, by various researchers from a couple of universities and companies like Google. And that actually created this transformers motion and large language models motion that we have today. And I encourage you to read about it more if you have not yet. GPUs, graphical processing units. I don't want to call it the heart, but it's the machinery behind any AI. And that's a piece of hardware without which it would not be possible to have any AI that we know today, because the computational power that you need cannot be coming from CPUs. That's why GPUs provide you with this power, and that's why companies like NVIDIA are growing like crazy nowadays. And finally, last but not least, is vector databases. And vector databases are powering the data piece for a lot of generative AI applications through vector embeddings. And we're going to talk about it on the following slides. But what you need to know is that vector databases are great for various search approaches like semantic search, visual, or multimodal search. And that's why it is one of the powers behind AI again. So when we talk about Linux, everything is a file. When we talk about Kubernetes, everything is a container. But when you talk about generative AI or AI in general, everything is a vector. And this is just the picture how DALL-E, one of their large language models, sees vector embedding. But in a nutshell, what you need to learn about vector embedding, that it is a numeric representation of anything. So it can represent the speech, it can represent text, video, whatever, in some numerical, multidimensional format. But the power of it is that it can also tell you the how close these numbers are to each other. For example, if you have cat and lion, then most probably in vector world, these two words would be close to each other. Or if you have multiple hundreds of articles about Kubernetes, and then you will search about Kubernetes, most likely you will find this article at the top of the top of your search, because vectors are going to search through it quite fast. That's what vector embeddings are, basically representation of any data in numeric format that can be easily comprehended and stored in the database, in the vector database. And this is the basic example of RAG, retrieval augmented generation. And RAG is the technology which allows you to actually create a chatbot, in short, right? So imagine you have lots of company data, proprietary company data. And this proprietary company data is about certain technology. For example, at Percona, we have a lot of data about databases on Kubernetes, and so on, right? What you do with this data is you put it into the vector database. And once you have it in the vector database, then you can easily search through it and find the semantic similarities. And what is happening next is someone is creating a question or writing a question to your chatbot asking, okay, how to install Postgres on Kubernetes. And what you get is you can actually contextually enhance this question with the data from PG vector easily and push it to some GPT or, some AI model like GPT-4. And as a result, what you're going to get is the response based on this data, proprietary data. And the power of it is that you quickly can get the detailed response about your question in a human readable format. And that is actually the magic of AI. So you ask about how to install Postgres on Kubernetes, and what you get is the answer about it. Like detailed answer, you need to do step 1, step 2, step 3, and it's in human readable format. I hope I did not mess it up and explained it quite easily, but that's what RAG is about. Vector databases, there are lots of them and various options. Some of them are open source, some of them are just new, like Pinecone is quite new, but it's already quite huge. It's very popular. Some of them, like FAIS, are open source, and they're like SQLite in the vector database world. And then the last but not least in this list is pgvector. And we're going to talk today more about pgvector because pgvector is just an extension for Postgres. And if you run one of the most popular open source databases today, then having a vector database is just enabling this extension. And that's quite easy and straightforward. And that's why I like it the most, right? But before we proceed, we have some quick poll. And if someone here runs databases in containers, please let us know by pressing the button A, B, C, or D. I hope you would not press D, which is like water containers. And I hope not a lot of C's as well, because we're talking here about databases in Kubernetes and DR for databases in containers. Shall we give a couple of minutes or 30 seconds? Okay. Kirsten, shall I just go to the next page? Or
Yeah,
how do I know that everyone is done?
Yep,
okay.
You should be able to see the results on the next page.
Okay, so confirm. Confirm means, yeah, everyone is running, which is great. Not a lot of no's, but some, not water containers. Okay, this is great. So we have the right audience here. And for those who are not running databases in containers, I hope we're gonna be able to change your mind, or you're just hesitant if you should be doing it. So let's see. So problem space. As I mentioned at the beginning, I'm the guy who is talking about the problems, right? So, and Paweł is going to talk about how to solve these problems. We're going to talk first quickly about Kubernetes operator. So for those of you who are not familiar with what is an operator, it's just a piece of software that runs within your Kubernetes and extends its API. So instead of creating stateful set, a pod, a persistent volume claim, so some basic Kubernetes concepts, what it allows you to do is to create any other object. In our case, it's Percona PG cluster object. You see this kind here. And what you do is you just describe what you want to get as a result. So it's the descriptive Postgres cluster in our case. You describe, okay, I want this number of replicas, I want this extension, I want my backups to go to this specific storage, and you just throw this huge YAML manifest with this description to Kubernetes API, and then operator does the rest. It provisions all the necessary resources, configures your database, and as a result, you get PostgreSQL with pgvector up and running in no time. And now you can also execute various day 2 operations. So yeah, now you have pgvector up and running in Kubernetes in no time, which is awesome. But now you have another problem. So you have your database in HA mode up and running, which is great. But what about the next step? What about if your Kubernetes cluster goes down? Or what about if the whole region goes down, right? And now you think about going multi-region. So multi-region is not only multi-region. Multi-region is also about multi-cloud or hybrid cloud, or in Kubernetes world, it actually boils down to two different Kubernetes clusters. So on the picture on the right here, you see there are two Kubernetes clusters, one on the left, one on the right, and each Kubernetes cluster has a Percona operator running there. And the way it works in operator world is that in each Kubernetes cluster, you have a custom resource. And you define your Postgres cluster for each of them, and then you somehow set up the replication between these two Postgres clusters. And that works, right? And actually, the main reason for disaster recovery, for the main reason for going multi-region is disaster recovery, right? When you want to be sure that there is actually no service disruption when one of your Kubernetes clusters or one of your regions is going down. Another reason is migration, right? So imagine you want to migrate from one cloud to another, or from one region to another, or from your on-prem data center to the cloud. That's another reason. And last but not least is what we love a lot is no vendor lock-in. Imagine you run on Amazon, and next day your company makes a decision, hey, we want to go GCP, or we want to go to Azure. And now you are in a situation where you need to move your workloads from, for example, from Amazon RDS to Google MySQL. And that's a lot of rework in a nutshell. But what Kubernetes is great for is that it provides you the standard APIs and allows you to avoid complete vendor lock-in. And now you can set up your application, you can set up your databases in a way that they use the same APIs, and you don't have any vendor lock-in. You can easily migrate from one place to another without changing anything in your CI/CD pipeline, in your application, anywhere. And that's another interesting concept called cloud ready. Is when you are running on-prem, but you make sure that your application and your infrastructure is cloud ready. And Kubernetes allows you to do that just like that. So if you have Kubernetes in your on-prem data center, then migrating to the cloud is just extremely easy for you. So when we talk about disaster recovery, there are basically 2 points that you usually need to take into the consideration. First one is recovery time objective, or RTO, is how fast do you recover from failure. So for example, if your data center fails and now you need to recover on your disaster recovery side, is it days? Is it hours? Is it minutes or seconds? So this is one of the major pieces of disaster recovery strategy, which is usually somehow enforced by the SLAs that your business give you. And another thing is a recovery point objective, which is more for the database, is how far away are you from your last transaction? So your application is writing to the database, writing some data. And at some point, your whole database crashes, or your whole data center crashes, right? So now you are switching to a disaster recovery site. Once you do that, are you sure that you have the last transaction that was written, or it's a few minutes behind? So recovery point objective is very important, and we'll talk a bit more about it on the following slides. But out of this slide, what I want you to remember is that these two concepts are the key ingredients of any disaster recovery plan in place. So if we talk about Percona operators, there is options how you set up your disaster recovery. And the basic one and the usual one is through backups. What it means is that you have Kubernetes cluster A, and in it, you are uploading your backups to some object storage, whether it is S3 or GCP or Azure Blob Storage, whatever it is. And you upload your backups constantly there, like daily, hourly, whatever your backup strategy is. Or you can even have write-ahead logs streamed there. And when your region crashes and your whole Kubernetes cluster goes down, what you do is you just run a restore procedure. So you recover from either full backup or roll on top of it some write-ahead logs, so your data is there. But the problem here is high recovery time objective. So depending on the amounts of data, if it's like multi-terabyte database, it might take you a lot of time to recover, because then loading the backup, recovering from it, it all takes time for sure. And then you need to reconfigure the application. So it all boils down to hours wasted, right? But for some companies, it's okay, because their disaster recovery protocols are quite relaxed. And we saw that in some companies it was almost 72 hours for disasters. And it worked for them, right? You can improve it greatly with operators as well. The way to do it is to use either streaming replication or continuous stream of write-ahead logs. So streaming replication is basically just taking data from one Postgres cluster to another through Postgres replication. And you can configure it through our operators as well. But what we mostly see is using continuous stream of write-ahead logs. The way it works is you have PG backrest instances in both clusters, and one cluster, main one, like here on the left, uploads continuously and streams continuously write-ahead logs to some object storage. And the cluster on the right, which is disaster recovery, fetches this write-ahead logs continuously as well, non-stop. So this kind of similar to streaming replication, but through an object storage. Why we see it more is because it's much simpler. It requires you much less configuration, and you can spin it up in a few minutes, and it does not require you to have networking figured out, because in case of streaming replication, you need to be sure that you expose your Postgres clusters so that they are reachable from one cluster to another, and that might complicate your overall setup. So it looks like problem solved. Sergey, you told us that you can recover quite fast, and the data is flowing almost continuously. And if you have a proper configuration for your database, you can get your recovery point objective almost to 0, right? So what is the problem? What are we solving here? And the reason is that it's not fully solved. There are lots of questions. First one is failover is not automated in reality, right? So yes, you have continuous flow of data from one data center to another, from one Kubernetes cluster to another. But what if this Kubernetes cluster fails? Who's going to perform a failover? Operator can't detect it. Well, it can, but you need a third agent for quorum to make a decision. Oh, yes, this is a failure. Now we need to switch the primaries, we need to switch the application, and so on. Yeah, and second point is point application to correct database. So does it require the configuration change, or is it going to be solved on the networking layer? How do you do that? It's not automated at all. And the last but not least is failback. So when you have a failover from main side to disaster recovery, what should happen when main side goes back up? Are you going to roll it back, or are you going to continue running on DR? So this is another question that is not really solved. And before we go into the solution phase, which Paweł is going to talk about greatly, we have another poll for you. So it's more about which disaster recovery technique do you currently use for your database. A, regular backups is the one with high RTO that I was showing. Replication is about streaming replication or going through this continuous write-ahead log streaming. Storage snapshotting is also quite close to regular backups, but it might be a bit faster because you do a storage snapshot, and if your storage allows, it will kind of recover much, much faster. And failover clustering is something I believe that Paweł is going to talk about. But yeah, if you're using it, it's great. And none is none, right? No disaster recovery is also possible. So let's see. Regular backups, storage snapshot. Oh, we have someone using failover clustering. That is great. That's awesome. Cool. Paweł, so stage is yours.
Thanks, Sergey. Hello, everyone. My name is Paweł Bojanowski, and as Sergey mentioned, I will try to show you one of the possible ways of automating the disaster recovery process. So as Sergey mentioned, we need kind of like God's eye view for the two separate clusters where we run our primary database and our standby database, as well as we need to somehow be able to reconfigure first the primary, then the standby Percona PG cluster. And we also need to be able to switch the traffic from the client application to the database as a part of this, as a last step of the disaster recovery process. And for that, as I mentioned, we'll need some kind of God's eye view, so we can modify both Percona PG clusters. We'll also need additional layer between the client application and the disaster recovery, and the database. And the reason for that is because we don't need to, we don't want to reconfigure all client applications. Instead, it would be great if we can just reconfigure the proxy or the layer that sits between the client application and the database. So our initial setup is we have two Kubernetes clusters, possibly in two different regions. So in the first one, we have Percona Operator, our primary Percona PG cluster. And in the second one, we have secondary, and the AJ proxy, which we'll use in this demo, is pointing to the Percona PG cluster endpoint in the cluster in US East 1 region. We'll also need some kind of monitoring tools, so we can detect either like a cluster or database failure in the cluster. So what typically happens, we have observability stack, and we'll define some alerting rules based on the metrics that we continuously collect from the clusters. And we can have alert in place, which will inform us that there are issues in our primary database cluster. For example, when the cluster goes down or the region goes down. So when the alert is triggered, we will need to first turn our Percona PG cluster primary in US 1 into standby mode. Then we'll need to promote our standby Percona PG cluster in US 2 to the primary. And as a last step, we need to reconfigure the proxy so the client application can still reach the database, but this time in the US East 2 region. And as I mentioned at the beginning, we need some kind of like God's eye view for our cluster fleet. And for that purpose, we'll use Nova. So Nova is a multi-cluster Kubernetes control plane that allows you to orchestrate workloads across multiple Kubernetes clusters. But at the same time, the Nova control plane is also a regular Kubernetes cluster, which means that you can interact with it using kubectl or regular tools. But having the Nova control plane gives us ability to interact with only one Kubernetes cluster to perform all the steps, which is reconfiguring the Percona PG clusters as well as reconfiguring the proxy. And our initial installation will have two Percona PG cluster object kinds, one for primary, one for standby, and we'll configure the schedule policy, which is Nova custom resource. And this policy will instrument Nova to schedule our Percona primary to the US East workload cluster and standby to the US East 2 workload cluster. Yeah, and Percona PG cluster custom resource makes it very easy to configure the standby and the primary. So the standby, so marking the cluster as a standby, we only need to set the spec.standby enable true in the Percona PG cluster manifest, and we need to set it to false for our primary. So let's talk about the proxy layer. So at the top, I have representation of my application that will talk to the database. And I want it to connect through the proxy. So the proxy will create the Kubernetes service. It will be configured with the config map. And it will forward the traffic to the endpoint of the Percona primary cluster. Okay, so I have a short demo here. So this is how you interact with Nova control plane. As you can see, I have two workload clusters connected, one in US East, the second one in US West. I've already deployed Percona PG clusters. So one of the primary is running in US East, and the secondary is running in US West, as you can see. I also have the HA proxy configuration in the Nova control plane. And as you can see, currently it points to the endpoint of the primary Percona PG cluster. So that's our initial setup. And now we need to talk about how we can plan for disaster recovery in this setup. So Nova control plane provides the way to configure where the workloads should run by using schedule policy, but it also provides a custom resource for recovery plan. So this is how you can define your disaster recovery steps. And you can also define when the recovery run should be executed. And you do that by matching the alert labels. So for example, if we have a Prometheus alert configured, which will fire when the primary cluster is down, I can send the label metadata in this alert. I can also configure the webhook in the Prometheus configuration to the Nova webhook. So whenever the alert is triggered, the Nova webhook endpoint will be called, and it will create the received alert object kind in the Nova control plane. And this will trigger the recovery plan I defined on the left-hand side of the slide. So the first step, we define when the recovery plan should be run. But there is also a steps section. So here we just define what should happen when the alerts when the Prometheus alerts us about the cluster failure. So as I mentioned before, first we want to make sure that we put our primary into standby mode. So this is the first step. We want to just patch the Percona PG cluster resource and set the spec standby enabled to false for this one. The second step is the opposite, but for the cluster 2. So the primary now will be promoted, sorry, the standby cluster will now be promoted to the primary. The third step is quite interesting because we'll need to reconfigure the proxy as well. So it points to the cluster, to the Percona Postgres database in the cluster in US East 2 region. But first we need to know the address, the endpoint address of Percona database in this cluster. So in this step, we'll read the address from Percona PG cluster object kind, and the address will be in status host field. It was visible in the first video that I played. So we want to read this address, and as a last step, we want to use it in the patch that will issue to the AJ proxy configuration. So from this point, we should be all set. It means that the standby will be now primary, and the user traffic should be switched to the standby. To the US East 2. And I have a short demo. So to simulate the client application, I have a Jupyter notebook that connects to the database over the AJ proxy. And we'll try to read from this database in a loop. And in the meantime, I will simulate the failure, and I will do that by creating the alert kind of objects in the Nova control plane. Yes, so this is the Jupyter notebook. We just try to select from the database with pgvector extension. As you can see right now, we can read the data successfully. And here is the alert that will get created when the Prometheus send the alert to the Nova endpoint. And once that happens, there should be a recovery run created, and we can follow whether the steps were executed successfully. So this is the recovery run kind of object in the Nova control plane. As you can see, the steps were completed successfully. And I think we can quickly verify that by checking whether the standby is now the cluster in US East 1. It seems that the cluster in US East 2 is now a primary. And we can also verify if the AJ proxy config got patched. It seems that it now points to the new primary, which is what we expected. And if we go back to the Jupyter notebook, there are no errors here. That's probably because I've added the sleep after each iteration, but there could be some transient errors when the AJ proxy is getting reconfigured. So we can talk a little bit about the schedule policies, because I just mentioned that there is such thing, but I guess we should talk a bit more about it, because they were instrumental in the initial setup. So the way the schedule policy is defined, you can match any kind of objects in the Kubernetes cluster. You can match them in the given namespace or namespaces. In this case, I want to only match object in one namespace, which is the PSQL operator. And I also want to match all the objects which has the label set to PSQL cluster equals cluster 1. And this is exactly the label I had on the Percona PG cluster 1, which was my initial primary. So this was the schedule policy for the initial primary. I also had another one for the standby cluster. I just used the different label selector. And the schedule policy also has the cluster selector section. So the cluster selector section, you can point to one of the workload clusters or multiple workload clusters. In my case, I wanted to run my primary in the cluster named US East 1 VLC. But even before we created these clusters, we needed to ensure that both clusters understand what the Percona PG cluster kind is. So before that, we need to have the custom resource definition in both clusters, as well as Percona operator running in both clusters. So normally you would probably just install the Percona PG operator in the two clusters separately, but you can also use Nova schedule policies to standardize your clusters. And by standardizing, I mean if you have tools or products that will be exactly the same in all of your clusters, you can use another schedule policy, and you can basically mention the list of clusters in the cluster selector, and you can use the spread mode duplicate, which means that you can only create the bundle of manifest once in the Nova control plane, as long as these objects match the schedule policy on the right-hand side, there will be created in each cluster. So I have the cluster selector when I select two clusters, but I also have the spread constraints with mode duplicate. And I can either duplicate, and I can either say, please create the copy of those manifests in each cluster. This is what I'm doing here, because for topology key, I picked the cluster name. But in a scenario when you have multiple clusters, let's say you have multiples in each region, and you want certain application to run in not in every cluster, but at least in every region, you can use different topology key. So in your case, the topology domain can be a region, not the cluster name. And yeah, as the same as before, we used the label selector. So the manifest on the left, it's Postgres Percona Postgres operator, and I had to label all the objects there so I can select them in my schedule policy. So this was for initial setup, but also in the disaster recovery process, when we patched the Percona PG cluster in Nova control plane, Nova scheduler made sure that these changes are synced to the workload cluster. And in the workload cluster, there was an agent which was responsible for syncing the status of these workloads to the Nova control plane. And thanks to that, we were able to read the endpoints of the both clusters because they were needed for our disaster recovery step where we were reconfiguring the proxy. And yeah, I think that's pretty much it. I want to thank you, and I feel I will just hand it over to Sergey.
Yeah, I'll hand it over to Kirsten. Yeah, on the screen here, you have two QR codes. One is leading, if you want, to Percona operators and our website. Another one is to Elotl website and talks about Nova. So if you want to learn more, feel free to scan those, and we're gonna get there. But I know we have some questions unanswered, so as promised, Q&A time.
Yep. So make sure you submit any of the questions that you have in that Q&A box in the bottom left-hand corner of your screen. A few have come in already. So Sergey and Paweł, are you ready? Do you see any performance degradation for databases in containers?
In short, no. That's the short answer. The performance for database in containers would be as good as on bare metal or in VMs, and it strictly depends on your hardware. There is obviously some components that might impact the performance, especially in Kubernetes, like container network interface plugins, CNIs, or storage, the way how you structure it. But if it is done right, you will not see any performance degradation. And we've done some benchmarks about it that we're going to share.
Great. What are the do's and don'ts for running databases on Kubernetes?
Okay. Well, let's start with don'ts. I think the biggest don't is to try to take your existing application and your existing database as is and expect that it's going to behave the same way on Kubernetes because, well, it is microservices and you need to think through, do you really want to migrate your monolithic application as is, or you want to first change its architecture a bit? So definitely change, right? For don'ts also, I would say we see companies are struggling a bit when they try to run databases on Kubernetes without any expertise in Kubernetes whatsoever. Yes, operators, they simplify day one, so deployment and management, day two operations. But if you don't know Kubernetes at all and do not have any in-house expertise in Kubernetes, then you still might face some issues because Kubernetes is quite a complex technology with lots of moving pieces. And yeah, I would not do that if you don't have it. For do's, I would say any platform engineer would definitely, and any platform team would benefit from running databases in Kubernetes because it's repeatable, it's easy to give it out to your engineers and development teams to run databases in K8s, easy to build any kind of UI or API on top of it. Another do's would be to, if you have a lot of databases, for example, you are currently running them in the cloud, like some RDS service, you would definitely benefit of running them in Kubernetes because it's going to be cheaper. And moreover, you would also get this benefit of then lock-in and simplifying your APIs because you will just use Kubernetes API instead of any other. That's on top of my mind.
Great. Your turn, Paweł. Can Nova itself handle zone and region failures?
Yeah, that's a question that comes up a lot, especially when we talk about using Nova for disaster recovery of other products. So Nova itself can handle zone failures easily because it can be deployed in highly available mode. And by that, I mean every Nova control plane component runs 3 replicas or 5 replicas, and we spread each replica so it runs on the node in different AZ. So this way we are able to handle the event when one of the zones fails. For region failures, we have the disaster recovery process for Nova control plane. So we can also deploy Nova control plane in a similar primary standby mode as Percona PG cluster, and in that case, when the primary fails, there is a way to switch to promote the standby to be a new primary. And yeah, I think in the upcoming release we'll also have a detailed documentation about how to do that.
Perfect. Another one has come through. Is Nova a bespoke solution for disaster recovery, or can it be used for other things?
Yeah, it can. So it can be used for managing the fleet of your clusters, for managing your workloads on top of the fleet of your clusters. So as I mentioned in the presentation, it could be used for standardizing your tooling in your clusters, as well as for cloud migration if you want to gradually migrate from cluster in one cloud to another. And you have Nova control plane managing that. It's quite easy to move your workloads gradually. It can be also used for availability-based scheduling. So you can think of the cases when you have fleet of your clusters, but only a few ones, let's say with GPU nodes, and you want to make sure that you will run certain workloads in the clusters with GPUs, because it's quite easy to kind of like juggle the workloads between the fleet of clusters with Nova. Can be also used for cluster upgrades when you don't want to upgrade your existing cluster in place, but want to provision a brand new cluster, kind of like on the side, and move your workloads there. And yeah, can be also used for disaster recovery, but we've talked about it already.
Great. It looks like those are all the questions that have come through. So with that, I would like to thank both Paweł and Sergey for this great presentation. If you are watching and you have further questions to ask, please do not hesitate to contact us. There's a contact us box on your console as well. Otherwise, thank you everybody for joining. Thank you again, Sergey and Paweł, and we hope to see you all at another webinar shortly. Thanks, everyone.
Thank you.
Thank you.